Hello everyone, my name's Logan. Welcome back to the lecture hall. Today we're covering our last lecture of the UCI Math 2A Single Variable Calculus course, section 4.9, Antiderivatives. So this is the last section of our course, and I'm really excited because we get to move on to what will be 2B, which is the second part of single variable calculus. And I like 2B a lot more because it's integrals and there's a lot more fun problems like finding volumes and stuff like that. So let's start with a definition. A function f is called an antiderivative of f on an interval I if capital F prime of x is equal to f of x for all x in I. So remember, upside down A means for all. And so what is this saying? It's saying a function is an antiderivative if it is equal, if this derivative of one function is equal to another. Okay, so that's not too bad. But what is it kind of intuitively? Basically, an antiderivative is taking a derivative and taking it back. It's moving the derivative and moving it back. So it's just the reverse operation. Okay, so now we have a theorem. If capital F is an antiderivative of lowercase f on I, then the most general antiderivative of f on I is f of x, capital F of x plus c for c in R. So what is that saying? It's saying the antiderivative of our function f of x, our antiderivative, we'll have a symbol eventually, derivative is equal to f of x plus c. But why do we have this plus c? Well, when we take a derivative of a constant, it goes away. So our antiderivative, this big f of x, may have been big f of x plus 6 is equal to, when you derive it, is equal to f of x. So that's why we have this plus c, because there's a constant, because when we differentiate, constants go away. So we have a bunch of commonly used antiderivatives, and derivatives are just moving backwards, is deriving backward almost. That's kind of what it is. So these should make relative sense. So if we have c times f of x, it's just c times capital F of x. So whatever your function is, if it's multiplied by a constant, your antiderivative will also be multiplied by that constant. If you add two functions together, like f of x plus g of x, their antiderivatives will just be equal to the antiderivative of f of x plus the antiderivative of g of x. Now, onto something that should make sense, and we'll go over this in 2b a lot more, but if we have x to the n, when n is not equal to negative 1, we get that the general antiderivative is x to the n plus 1 divided by n plus 1. So it's like reverse power rule. You add 1 to the power, and then you divide by that power. Then we have 1 over x is ln of the absolute value of x. The absolute value bars are very important, but we should know that the derivative of ln of x is equal to 1 over x, so it makes sense that the antiderivative of 1 over x is equal to ln of x. Then we have e to the x. Well, differentiation, nothing changes, so antidifferentiation, nothing changes. The e to the x, the antiderivative is e to the x. B to the x is equal to b to the x divided by ln of b. Cosine of x is equal, the antiderivative is equal to sine of x. And sine of x, is the antiderivative of sine of x is negative cosine of x. So it's a little bit of a flippy flop. The derivative of sine is cosine, but the antiderivative of sine is negative cosine. Then we keep moving on. If we have secant squared x, its antiderivative is tangent x. Why is that? Well, because the derivative of tangent x is equal to secant x squared. And then we keep going. Secant x tan x, the antiderivative of that is secant x. The antiderivative of 1 over the square root of 1 minus x squared is sine inverse x. And then the inverse, or the antiderivative of 1 over 1 plus x squared is equal to tan inverse x. So these are antiderivatives. And this was a very short section, just went through, you know, one definition, one theorem, and this stuff. But there will be a lot more antiderivatives in the form of integrals for our Math 2B course. So I really do appreciate that you guys watch these lectures. Hopefully they help. If you'd like me to explain things better, do more questions at the end, whatever it may be, please put it in the comments so I'll actually know what you guys want to watch. So that is all for the lecture portion. Let's transition into the practice problems. Okay, we're doing 3 problems today. We're doing number 1, 9, and 20, and you will be doing way more of these if you do 2B, which you should. 2B is a fun class. Alright, let's start. This says, in the textbook it says, solve the general antiderivative. So what does that mean? Well, you have to add plus c to basically everything we do. So we're moving backwards, and we see, okay, 4x plus 7. This is equal to saying 2 times 2x plus 7. Why do I change that? Because we have to power rule this, and if you remember, it's x to the n, its antiderivative, like its AD, is equal to x to n plus 1 over n minus 1. So we have to take away, because it's x to the power of 1 right now, so we have to take away a 2, and then we have to divide by a 2. Well, we're taking away a 2 and just putting it up top, so we get that that's equal to 2x squared. And we can check it, because if we do the derivative, we get that that is equal to 4x. But then what about 7? What is it? Well, it's a constant, but you can kind of think of it as x to the 0, right? So then you pull out a 1 somewhere and divide by 1, right? And add 1 here, right? And it's just now 7x. 7x. And if you did the derivative, you would get the derivative of 2x squared plus 7x is just equal to 4x plus 7. Okay, now on to number 9. This one's kind of a throwaway question because it's very... Oh! Forgot something. Plus c. All general antiderivatives have to have plus c. I said that before I even did this question. I just forgot. But you will lose 1 point, 2 points, maybe even 3 points depending on the professor if you do not write your plus c. Okay, now the throwaway question. I call it a throwaway question because it's really easy, but some people might just write 0 because they think they're doing the derivative and they just see, oh, a constant, root 2. That's a constant. Oh, the antiderivative is just equal to 0. No. The antiderivative is just equal to root 2x. Why do I say this? Because you can look at it just like the 7 here. You look at this as root 2x times x to the 0, and then you just divide by 1 and put a 1 up here, and you just get it's equal to root 2x. Now on to 20. 1 plus 2 sine x plus 3 over root x. Well, we know the antiderivative, I'm just writing AD, is equal to x because this is just 1. So every time you see a constant and you're trying to find the antiderivative, also that's root 2x plus c. I forgot yet again. Jesus. Every time you see a constant and you take the antiderivative of it, it's just going to be that constant times x. Okay, so times, or plus 2 times, what's the derivative of, our antiderivative of sine? Well, we know the derivative of sine is cosine, so that means the antiderivative of sine is negative cosine, so times negative cosine. Okay, and then plus, well, what is this 3 over root x? What is this also equal to? This is equal to 3 times x to the negative 1/2. Okay, that's not bad, but we have to add a 1, right? And we divide by 1/2. Why do we divide by 1/2? Because the antiderivative, if you have x to the n, it goes to x to the n plus 1 divided by n plus 1. Well, what is n plus 1? It's just going to be 1/2. So then we get this as plus 3 over 1/2 times x to the 1/2. Well, we can rewrite this whole problem out. It's just equal to x minus 2 cosine x plus 6x to the 1/2 plus c. And you always write that plus c. I know this is the third time I'm saying it. Always write plus c. And so this is the general strategy for antiderivatives. You just move backwards. We do everything that we've been doing for the past 20-ish videos. I don't know how many I've made. But instead of going derivative, do antiderivative. Okay. So, yeah, I've already said basically everything I wanted to say. Thank you for watching the videos. It makes me happy. As always, my name's Logan. Thanks for watching. Have a great day.